In the previous video, I was talking about application of elasticity, correct? Let's discuss couple of them. See, the first one is a very simple one. The machine, whatever the machines you see, here the metallic objects you have, right? They should never be put under tremendous stress. Okay, if that happens, they will permanently deform. This is especially true in vehicles because the engine of every vehicle is a metal, correct? It's a metallic part. Now, inside the engine, there is a lot of stress and pressure and everything because the engine has to work, especially, when you accelerate and all, there's a lot of stress and pressure, correct? Now, the machine is designed in such a way that those metallic parts in the machine, they are never under extreme stress because if they deform once, you cannot put it back in its original position. Understood, right? This is one of the use where elasticity is important, or application where we have to use elasticity. Like, say we are talking about stainless steel piston inside an engine. I cannot put it under a stress more than 3 into 10 to the power of 8 Newton per meter square. If that happens, then the engine will permanently get blocked. Okay, basically the machine goes like it's gone. You can't do anything. This is one of the applications. Another application of elasticity, this is a very important one. That is, see, you must have seen in most of the buildings under construction, you have huge cranes, correct? And if you look at it, those cranes will have one steel cable coming down and they're going to lift huge, heavy loads are being lifted, correct? Now, in this case, we have steel. We use stainless steel cables, or you can call it as stainless steel wires. Now, what should be the radius, the thickness of that wire so that it can carry the load? Because length is going to be like very long, you know that. But what should be the thickness? Now, here elasticity plays a very important part. Because elasticity, the stress, whatever you are going to apply on the body. And because of the stress, what is the strain, which is developed in the body? These things play a very important part. Understood? Now let's do it mathematically, like what we are going to do here. It's a very simple calculation. It's more of a logical calculation what we are looking at. Generally, for a crane, or any of these kind of cranes, the load is around 10 to the power of 4 kg, or you can call it as 10 metric tons. 1 ton is 1000, 10 metric tons. Now, if a crane which is having a stainless steel cable has to lift a load of 10 to the power of 4 kg, we have to look at what should be the radius, okay, the thickness of the wire. For that, what we know the stress of the steel, correct? The stress or the ultimate breaking stress of the steel is 3 into 10 to the power of 8 Newton per meter square. Correct? Acceleration, let's take it as 10 meter per second square, easy calculation. Now, if a body has a mass of 10 to the power of 4 kg, the load is 10 power 4 kg, then the weight acting on it will be m into g, correct? And weight is a force, isn't it? Now, what will be the stress? Ultimate breaking stress is equal to force per area of cross section. Force is what? mg, the weight, divided by pi r square, isn't it? Let's apply the numerical value. You have 3 into 10 to power 8 is equal to 10 power 4 into 10 by 22 by 7 into r square. We need the value of r. So r square is equal to 7 into 10 power 4 into 10 by 22 into 3 into 10 to the power of 8. Now, R value is approximately 1 centimeter. Like if you do precise calculation, you'll get 1.03. Take it as 1. Now, if you look at it, 1 centimeter radius stainless steel cable can withstand 10 to the power of 4 kg of load. Correct? Now, that's why in cranes and all these places, what they do, they use bundles of steel wires. It's not one wire, it's bundle of steel wires. In the sense, they can carry a lot more than 10 to the power of 4 kg. or 10 metric tons. Okay, you see why this elasticity is important. How much the crane can bear, that load, whatever you have. To figure out that one, we need to find the elasticity, or this is where elasticity is required. All right, let's look at another example, very practical one, which is construction of bridges. Guys, whenever you talk about a bridge, it's connecting from one place to another place. So stability is important, correct? That means bridges are designed in such a way that it should not bend, it should not break. Not only that, it has to withstand that traffic load, or it also has to withstand the swaying of the wind, the force from the wind, and even the weight of its own structure, isn't it? A bridge has to be designed in these particular ways, as in there are certain conditions. All right. Now, what we have in a bridge. Now, look at this particular figure. See, for a bridge, you have length, breadth, and depth. Correct. Depth in the sense the thickness, whatever you have. Length and breadth, obviously, very important. We have 2-lane bridges. We have 4-lane bridges. The breadth, very important. And the depth is also very important. The reason is, whenever there is a load which is being applied on the bridge, the weight, you can see that in the figure. The bridge is going to have a depression. Depression is delta. Okay, that depression is very important, because if the depression becomes too much, then the bridge will break. Now, what should be the elasticity, so that we can calculate what is the maximum load bearing capacity for the bridge? All right, what should be the elasticity? Now, here we have a simple formula to calculate the depression. Delta is equal to WL cube divided by 4YB d cube. See, if delta value has to be lesser, then Young's modulus should be more, or breadth of the bridge has to be more, or depth of the bridge has to be more, correct? Now, if you look at these three, Y, B and D, D plays a major role because you have D cube, right? So what we do, we increase the depth of the bridge. See, you cannot directly increase the depth of the bridge, because the bridge is going to bend otherwise. That's why what we have is, there are different structures. Like we have letter I-shaped beam. Okay, now I-shaped beam, we use this girder. So this has, more load bearing capacity. Understood? Now this is going to stabilize the bridge, as well as the depression, whatever you have, that is going to reduce. All right. Now here directly we are using the modulus of elasticity, correct? Because if the bridge is very elastic, that means the bridge will sway when the wind comes. Or if there is a lot of traffic on the road, then the bridge is going to have a lot of depression. That's why what we do is, we make use of this modulus of elasticity and figure out how the bridge has to be designed. All right, another important example, correct? Now, another example or application what we can think of is, more of, I would say, a general example, I would say. See, any particular planet has mountains, obviously, correct? Earth, if you take any planet, it has mountains. Now, we can figure out an approximate value of the highest mountain structure on a particular planet. All right, for that, we use elasticity. Okay, very strange, but still it is true. We use elasticity because the material on a planet, it is what? Rocks and boulders and sand and mud, these kind of things, correct? They have elastic property. Okay, now we make use of this and we can figure out what is the tallest structure on that particular planet. Okay, let's talk about Earth itself. Now, what you have, imagine you have a mountain. At the base of the mountain, you have a lot of pressure, correct? You have tremendous pressure, the entire weight of the mountain. What is pressure formula? P is equal to rho GH, isn't it? Now, approximately the density is going to be 3 into 10 to the power of 3 kg per meter cube, for the material, for the rock. All right, this is the density, mind you. And G, you can take it as 10 meter per second square. Correct? Now, see, at the bottom of the mountain, you have rocks and boulders and these things. Correct? They have a particular elastic material, elastic property. Correct? Now, the elasticity or the modulus of elasticity for a rock is around 3 into 10 to the power of 8 Newton per meter square. Okay, now this is the elastic limit, you can call it. See, if elastic limit is so much, 3 into 10 power 8, the pressure has to be less than this, correct? Because if the pressure becomes more than the elastic limit of a particular material, it will collapse under its own weight, correct? But mountains are very stable. They have been here for millions of years. If mountains are very stable, that means the pressure, whatever you have at the bottom of the mountain, has to be less than the elastic limit, whatever we have for the rock or the boulder, whatever we have. Correct? So P is less than 3 into 10 to the power of 8. Rho G H is less than 3 into 10 power 8. So H is less than 3 into 10 power 8 divided by 3 into 10 to the power of 3 into 10. Correct? Now H has to be less than 10 to the power of 4. 10 power 4 is what? 10 kilometer. That means the maximum height a mountain can have on earth is less than 10 kilometer. And the tallest mountain is Everest, which is around 9 kilometer. Correct? So this is another application where we can figure out the elastic property of the earth or elastic property of the rock or boulder and figure out the structure, what will be the highest or the tallest. Understood? Now, to sum up whatever the applications we have done, the first one is about machines. You should not put it under a lot of stress, otherwise there's going to be permanent deformity. Correct? Second one is about the cranes. We use steel cables to lift up what should be the radius. Third one was the bridges. What material do we use, or what should be the modulus of elasticity so that the bridge is stable. Third one is the tallest structure in a particular planet. All right, now these are applications of elasticity.